Okay, now we're going to do some examples of calculating hypothesis test. So the first example we're going to do is one where we're going to suppose that the sample or the population mean is 24 versus the alternative hypothesis that the mean is less than 24. And we're going to assume that we have a sample average of 22.5, a sample standard deviation of 4, n is 25, and then alpha is 0.05. No matter what approach we take to doing this hypothesis test, we will always need to know what the t statistic is that goes along with it. So we're going to go ahead as our first step and calculate t is x bar minus mu naught over s over the square root of n. Mu naught, remember, is the hypothesized mean that we have. So in this case, it's going to be 22.5 minus 24 over 4 over the square root of 25. So I get minus 1.5 over 0.8 which gives me minus 1.875. So that is my critical value. What that means is that if I assume that the population mean is 24, I would need to walk 1.875 steps to the left of that mean in order to get to my observed value. With the classical approach, what we'll do is we'll come up with a critical value. Because this is a one-sided test, all of my error will go down in the left-hand tail. So I know in my t table, I'm going to look in the 0.05 column. I had n was 25, so that gives me my degrees of freedom is 24. So I'm going to look in the 24 row. Under the 0.05 column. So I'm going to look in the 24th row. Under the 0.05 column. And I see 1.711. So t sub 0.05 comma 24 is 1.711. So that says that I could be up to 1.711 steps away from the mean before I would see a problem. Well, since minus 1.875 is less than minus 1.711, since going out (1.875) steps to the left is more than going 1.71 steps to the left, we reject the null hypothesis. The p-value approach would say, go to our table, go to the 24 row, and look for my critical value of 1.875. You remember, since this is symmetric, I don't need to worry about the sign. The sign just tells me which direction I'm moving. I'm going to go to this 24th row, and I'm going to see where 1.875 would lie. Notice that's between 1.711 and 2.064. So I know that the p-value is somewhere between the two column headers of 0.025 and 0.05. So I know that the p-value is between 0.025 and 0.05. Since the p-value is less than my alpha level, we will reject the null hypothesis. Let's take another example. Let's suppose that we have a null hypothesis that the mean is 137 versus the alternative that the mean is greater than 137. We're going to again use alpha as 0.05. Suppose we've taken a random sample and that sample has a sample average of 140.2 and that the sample standard deviation is 10 and that n is equal to 16. I want to know if I will accept or reject the null hypothesis or fail to reject the null hypothesis. Again, in order to do that, I need to look at my observed value of 140.2 and say how likely is it that I would have observed this value given that the null hypothesis was true. So I need to calculate the probability of observing this value in a t-distribution with a mean of 137 and a standard deviation of 10 over the square root of 16. Right? In other words, our first step is still the same. We're going to calculate the t-value, which is 140.2 minus 137 over 10 over the square root of 16, which gives me 2.8 over 2.5. How about if I do arithmetic correctly? $140.2 minus 137 is 3.2, which gives me 1.28. So I know that that's my t-value, that an observation of 140.2 is only 1.2 standard deviations above this hypothesized mean of 137. So let's look at our critical value. Again, because this is a one-sided test, I'm putting all the probability into one end. I'm going to use the 0.05 column again. So I'm going to use the 0.05 column, and I'm going to have 15 degrees of freedom because n was 16. Oops. Not sigma 16, this was n is 16. Okay. So that gives me the degrees of freedom is 15. So I'm going to go to my t-table. I'm going to go to the 15 row, the 0.05 column, and I see 1.753. Since this was 1.753, well, 1.28 is not greater than 1.753. So we fail to reject. Okay. A critical value of 1.753 means we would need to be more than 1.753 steps above the mean. We were only 1.28 steps above the mean. We did not go out far enough for this to be considered a rare event. So how do we do the p-value now? Well, we're going to go back to our t-table, so this p-value approach. We're going to go back to our t-table. We're going to look in that 15 row. I'm going to find where 1.28 lies along that row. Notice that it lies in between these two columns. 1.28 is more than 0.69, but it's less than 1.341. So I know that the p-value is somewhere between 10% and 25%. So the p-value is somewhere between 0 and 25%. Because the p-value is greater than 0.05, that means we fail to reject. Again, notice that it doesn't matter which way I do it, either the classical approach or the p-value approach, both of them fail to reject. That should always work out that way. It shouldn't matter if you use the classical approach or the p-value approach. You should always come up with the same conclusion. Okay, let's look at one more example. Let's say we're hypothesizing that the mean is 92 and our alternative is that the mean is not 92. Again, we're going to use alpha's 0.05. And let's suppose we have an x bar of 89.3. S is equal to 12, and N is equal to let's do 51. Okay, well, first of all, note that we have N is 51 is going to tell me that my degrees of freedom is 50. Alpha is 0.05 tells me I'm going to look in the alpha over 2 or 0.025 column. Why do I look in the 0.025 column in my table rather than the 0.05 column? Well, this is a two-sided test now. I'm not giving an indication of direction. I'm just saying that I think the mean is not equal to 92. So I could either go out too far to the right or too far to the left. So I need to split my error of 5% into the two possibilities, leaving me with 2.5% on one end and 2.5% on the other. Again, we want to come up with a t-score, so we're going to come up with a t-statistic by looking at x bar minus mu naught over s over the square root of n, which in this case is 89.3 minus 92 over 12 over the square root of 51. And if I do that on my calculator, get minus 2.7 over 1.68. So I get minus 1.607. I'm now going to look up at my t-value of 0.025, comma, 50, and I will see that that is equal to, in the 50 row, I want the 0.025 column, which is going to give me 2.009. So I know I'm really looking at plus or minus 2.009. Right? I know that I could either go out to the right 2.009 steps before there would be a problem, or I can go out minus 2.009 steps to be a problem. So I can either go right 2.009 steps or left 2.009 steps. So if I exceed this value either way, I'm going to reject the null hypothesis. So what I'm looking at is here's minus 2.009, and here's 2.009. I'm going to reject if I'm in either one of those regions. Well, minus 1.607 is in between those two. So we will fail to reject the null hypothesis because it did not exceed the number of steps I can move at left or right. Well, now let's look at the p-value. I'm going to go back to my t-table and look for 1.607 in that 50 line. And I see 1.607 is somewhere between 1.299 and 1.676. So that means my p-value in one tail is somewhere between 0.05 and 0.10. So one tail has probability between 0.05 and 0.10. So total p-value is twice that. So we know that 0.1 is less than p is less than 0.2. Again, we know that in one tail, my p-value is somewhere between 0.05 and 0.10. But one tail only takes care of half of the possibilities. In order to get all the possibilities, I need to include that I could go out either direction by 1.607 steps. So that would double this interval to between 0.1 and 0.2. In a one-sided test, I just have to come up with an interval based off of this one value, because all of the error is shoved to one side. In a two-sided test, because the error can happen on either side, I have to take that p information I get from the table and double it to get the p-value associated with the test. Again, because p is greater than 0.05, we will again reject the null hypothesis. What's one of the advantages of a p-value rather than the classical approach of comparing to a critical value? Well, the p-value gives me an idea of the strength of my argument. The smaller p-value is, the more strongly we can reject the null hypothesis, because the p-value measures the percent of the time we would have observed our sample given the null hypothesis was true. We've set a threshold that we would need to observe that less than 5% of the time in order for there to be a problem. Well, this says we would observe it between 10 and 20% of the time. That's not an anomaly. So therefore we cannot reject. On the previous problem, or on problem 1, our p-value was less than 0.05, somewhere between 0.025 and 0.05. That means that it happened less frequently than could be explained just by random chance, so therefore we would reject the null hypothesis. If I would come up with a value of 0.0001 for my p-value, which can often happen in practice, that's a very strong rejection of the null hypothesis. Well, hopefully these examples will help you do the hypothesis testing portion of your homework.